Welcome to the presentation of our paper entitled Using Mutation Testing to Measure Behavioral Test Diversity. My name is Francisco Gomes and I am a senior lecturer in software engineering at Chalmers and the University of Gothenburg in Sweden. Now, allow me to share how Felix, Robert, and I were able to use mutation testing to advance diversity-based testing. So, let's start with diversity. So diversity has been proposed as a key criterion to improve the test effectiveness. Intuitively, we perceive test cases as diverse if they are different from one another. Many testers use this idea to design or choose test cases. The reason is because we assume that two tests that are similar are likely to reveal the same fault. Hence, we want to optimize in variety, hoping that by covering different parts of our code, we can cover different faults. However, typical test diversity approaches rely on artifact data to detect the similar test cases. Examples of this data is test input, test output, test specifications or scripts, among other things. Note, however, that all those pieces of information, they are related to the test specification and are static, meaning that they do not necessarily capture the behavior of the system under test, which is really connected to test failures. In turn, mutation testing is a powerful tool that allows us to instrument and collect data on the actual behavior of the software. Therefore, we aim to use mutation testing to expand diversity measures to go beyond artifactual data and actually measure the diversity of test behavior. So, before I go into details, the four main questions driving our research are: first, we want to investigate how to represent and capture behavioral data. Then, how to instrument mutation testing to calculate this diversity information. Our goal is then to compare the effectiveness of artifact and behavioral diversity, and lastly, identify the advantages and disadvantages of our approach. In a typical diversity-based testing pipeline, we would measure the distance between all pairs of test cases and store it in a distance matrix that can then be used for various purposes, such as prioritizing tests. We introduce mutation testing prior to this pipeline to generate behavioral information by running all tests against several mutated versions of the system under test. We store this information in a structure called test outcome matrix and measure distance between rows of this matrix by comparing pairs of co-execution results and identifying patterns with consistently similar test outcomes. Details of those measures and calculations are presented in the paper with a small example. Here, we focus on our assumption that test cases that fail or pass together against the same mutated versions are more similar than those tests with contrasting outcomes, and therefore reveal similar faults. We verify this assumption in our evaluation. Now, we evaluate our approach in an experiment where we compare behavioral and artifact diversity to prioritize test suites from 6 different open-source Java projects. In order to measure b-div with mutants, we use PIT to instrument the mutation of the projects. For artifact-based diversity, we calculate the normalized compressed distance between different JUnit test methods. Finally, our goal is to see which technique can kill more mutants with fewer tests. So we also compare with a random prioritization of tests and also a greedy approach that we've implemented that knows the maximum number of mutants that can be killed by executing a specific percentage of the tests. Now, here are our results. Ideally, we want to quickly reach the top, meaning that we could review all mutants with fewer tests. These are the results that we obtain for each of the 6 projects. Overall, b-div test prioritization using behavioral metrics converged the fastest across the board, and even on par with the greedy algorithm that acts as an approximation of the best possible prioritization. For brevity, we'll focus on a few highlights of our results. So first, the improvements are significant according to our statistical analysis. For instance, if we take the MP3 a-div project, we are able to detect 90% of all mutants by executing only 30% of the tests. We also saw that smaller test suites, they hinder artifact diversity. For instance, both APK parser and sorting algorithms are projects that have less than 15 tests, and a-div in those cases perform worse than random. The reason is because there isn't enough information in the different tests to perhaps convey a meaningful diversity between the tests. However, b-div still performs as good as the greedy approaches for the small projects and the big projects. The distinguishing factor between those two small projects, in this case APK parser and sorting algorithm, is that number of mutants generated for APK parser is much larger than the number of mutants generated by sorting algorithms. Therefore, b-div will have way more columns to be able to capture and extract the different patterns of test behavior that one project has in comparison to the other. We also noted in our results that mutants created by different mutation operators are more often killed than others. For instance, out of the roughly 30,000 mutants killed throughout the 6 projects, mutants based on the invert negatives mutator were killed only 4 times, whereas the mutators for removing conditionals and the non-void method calls mutants were killed more than 2,000 times each. That may simply be due to the nature of these projects, but in future work, would like to investigate further whether there are interesting connections between diversity and actually mutation operators. However, we also noticed a few limitations with our approach. A few highlights are that the approach heavily depends on the quality of the mutation tools. Not only if the mutation is done properly, but also the number of mutation operators available, and of course, how these different mutants are created. So for instance, since the behavior is extracted from the mutants, one must be mindful of risks with redundant mutants or subsumed mutants. Lastly, the approach took a lot of time. The biggest project, which was J-free chart, took 30 hours to run such that we could obtain the test outcome matrix. The reason is because we need to run all test cases against individual mutants to know the behavior of all tests. In contrast, we only need the test outcome matrix, the TOM, we only need it once, and then we can update it on demand. We can reuse the behavior information to keep training the approach to identify the test diversity. So let's return a little bit to our research questions and summarize our findings. First, we capture behavioral diversity by analyzing tests that consistently pass or fail together against mutated version of the system under test. Moreover, we can use mutation tools to automatically create several mutated versions of the set to identify which tests fail together for each mutant. The result is a test outcome matrix that's used to calculate the distance matrix. In terms of our evaluation, we'd noticed that a-div and b-div indeed differ in terms of effectiveness. Behavior diversity is consistently better at revealing more mutants with fewer tests. Our analysis reveals an average improvement in effectiveness between 19 and 31%. In terms of trade-off, b-div is more effective. On the other hand, there is a dependency to the mutation tool, as well as the number and types of mutants created. Also, scalability becomes an issue for larger projects. I would say that this research opens the possibility for a variety of investigation pertaining both diversity-based and mutation testing, and that is one of the most interesting aspects of this project. We can apply and compare b-div in different test activities such as test optimization or test visualization, and explore the complementary aspects between a-div and b-div. In connection to mutation testing, we intend to investigate this relationship between diverse tests and different mutation operators, trying to identify whether specific operators yield more or less diversity in a test suite. Alternatively, we could use test history to apply b-div. However, there are many issues inherent to using historical data. Besides availability, there may be flaky tests or very uneven failure distribution such that the noise-to-signal ratio is small. Hence, mutation testing can be a great surrogate for history-based approaches. Lastly, both diversity-based and mutation testing approaches have limited scalability, so improving inefficiency in this pipeline is something that's needed to allow transfer of this technology to large-scale software testing. And that covers the main points of our papers. If you're also interested in the topic, feel free to contact us with possible questions or even ideas for collaborations in research projects. With that, stay safe and thank you for watching.